I think it's nearer 5 or 6, I think. That one there. Okay then. Okay, so just a very quick 2-minute review on what we did last week. So last week we looked at this object here, which is equation 1.56. This is on page 9. This is what we call the small increments formula. Okay. The small increments formula here presented in its two-dimensional or two-variable case. So this tells you what the change in value that a function undergoes. It expresses that change in value in an approximate form as a linear combination of the changes in value of the input variables. So the delta x and the delta y there are the changes in value in the variables x and y. So the change in the value of the function is approximated as a linear combination in the changes in the values of the variables, and the coefficients in that linear approximation are provided by the values of the respective partial derivatives evaluated at the starting point. Okay? So whatever base point we're talking about, that these small changes are small movements away from whatever that base point is. Now we'll return to this kind of idea shortly when we look at Taylor series for functions of 2 or more variables. But this expression is, in a sense, the best possible linear combination of the changes in x and y. These coefficients here, df dx and df dy, those are the ones that do the best job at approximating the change in value of the function as a linear combination of changes in x and y. And the approximation is better the closer to the base point you are, in general. So as the delta x and the delta y become very small, this approximation to the change in value of the function becomes better and better. Now the example that we looked at last time was this one based on the movement of a simple pendulum. The movement of that simple pendulum is governed by this equation here, which relates the length of the pendulum and the time taken to complete a full period in its motion. So from one side all the way over to the other and all the way back, that's one full period. And this expression here, 4 pi squared times L over t squared, should approximate the acceleration due to gravity wherever this pendulum is. Okay, so this equation, this functional relationship between L, t, and the gravitational acceleration, this comes to us from the physical principles. But we can regard this as a function for g, so it's telling you what g is in terms of L and t. So it's a function called g of L and t. And we can apply the small increments formula to it with this kind of expression here. So I'm moving quickly through this because we discussed this last time. So here's the small increments formula here, except I'm taking absolute values of both sides. The reason I'm taking absolute values on both sides is the context we're working with this is where we've carried out an experiment and we've measured the length of the pendulum, we've timed the time it takes to complete one period of its motion. We get readings of 2 meters and 2.84 seconds, but of course in any kind of real world measurement situation, there are always uncertainties associated to our measurements, I guess, unless we're counting, some discrete number of times something has occurred, you might get the exact value. But if you're measuring some continuous quantity, be it length or be it time, there's always a natural inaccuracy associated to that, due to, for instance, the uncertainty about the precise calibration of your measuring instrument. Okay, so we'll suppose that we know the length within an error of 2 millimeters, 2/1000ths of a meter, and we're supposing we know the time, 2.84, within an error of 100th of a second. What the small increments formula can tell us is it can approximate for us what the associated error, so here the delta G, the delta L, and the delta T, those are denoting the errors in measurement. The small increments formula can allow us to get an upper bound, some expression of how bad the error in the approximation of G could be. So what's the effect of these errors in L and T? How do they feed through the formula and produce errors in your estimation of G? Well, taking absolute values, using the triangle inequality to say that this absolute value is less than or equal to the sum of the absolute values. Here we see the partial derivative expressions, 4 pi squared over t squared and 8 pi squared L over t cubed. Those are the partial derivatives dg dl, dg dt, respectively. And absolute value delta L, absolute value delta T, those are bounded above by 2,000ths and 100th, respectively. Okay. And that combination produces this upper bound, 0.079, approximately 800ths. That's the upper bound for the error in G. So we can say then that our prediction of the value of G is the exact value we get out of the formula, putting in L and T as their claimed measurements. We get an approximation of 9.79 meters per second, and this is some quantification of how bad we think the error could possibly be, based on the errors in the measurements of L and T. Okay. So that example we discussed last. There's a similar example shown here over the page, which I'll let you to read. I'll just quickly talk through it. So this isn't, in this example, we're not talking about errors in measurements, but we're talking about percentage changes in some of the variables. So in this example, we were looking at how the resistance R of a section of wire, how that depends on the parameters, on the two main parameters of the wire that are relevant for the resistance. Okay, now we're not electricians or anything, electrical engineers, so we're not going to go into the physics of this, but it's not hard to get the feeling that the resistance of a piece of wire, so its resistance to electrical current, depends on two things. So the resistance is how hard the electricity finds it to flow through the wire. Well, one thing is that the longer the piece of wire, the harder it is for the electricity to flow through. Okay? So the resistance has a dependence on the length, L, and it also has a dependence on this quantity, A. A is the cross-sectional area of the wire. You just slice the wire, cross-section is a circle or a disc, and the question is, what's the area of that? So it's to do with how thick the wire is, how thick or thin the wire is. Okay. The thinner the wire, the more resistance it has. It's very intuitively, very naively, there's less space for the electricity to move through. That's not the correct explanation, but intuitively it's something to do with that. Okay. So the smaller the cross-sectional area, the higher the resistance R. Okay, so that's expressed here that we have the dependence of 1 over A, 1 over the cross-sectional area into the resistance. Then there's also this coefficient here, rho. Are you trying to close it? Or? Yeah. You failed. Do you want to try again? Okay, it's not our fault. Okay, so the other component here is this quantity rho here. Rho is what's called the resistivity of the material. So you understand the idea, hopefully, that different materials have different inherent resistances. So copper, the reason copper is used for all our electrical wiring is it has quite a low resistance amongst all the other possible metals that we might use, available metals that we might use. But there are things that conduct electricity even better than copper, of course. The reason we don't use them for wires is they're not as abundant or cheap or suitable for the other aspects that wires have to do. So from the physics of the situation, we have this functional relationship between the two parameters, L and A, of a section of wire and the resistance of it. So we're assuming that our wire is some particular kind of material. So the resistivity rho is fixed. So what we'd like to do is use the small increments formula to assess what the change in resistance is going to be if the cross-sectional area and the length change. Okay? So we'll suppose that the cross-sectional area decreases by 1% and the length L increases by 2.5%. Now both of those effects will increase the resistance of the wire. Because the wire is longer, there's more of it that the electricity has to flow through, and the wire is getting thinner. The cross-sectional area is decreasing. But can we quantify, using the small increments formula, what the resulting change in the resistance would be? So that's done over the page. So it's a straight application of the small increments formula. Delta R is dr dl delta L, dr dA delta A. The partial derivatives come out as dr dl is rho over A, dr dA is minus rho L over A squared. And the length is increasing by 2.5%, so the change in L is 0.025 L. And the change in A, well, A is decreasing by 1%, so its change is minus 0.018. So this is what it looks like here, but because we have this extra factor of L and A, they go with the partial derivatives here, and they reform the resistance R. Okay? Resistance, remember, was rho L over A. So again, we get rho L over A, rho L A over A squared, so rho L over A. And we see the combined effect is 0.035 R, so it's a positive quantity, so it's an increase, and it's a proportion of R, so we can express it as a percentage change. It's 3.5%. Again, it's just a nice illustration of the utility of these partial derivatives. Okay, so those changes in L and A, the length and cross-sectional area of the wire, lead to a 3.5% increase in the resistance. Okay. So the exercises on page 12, you might have done some of them in last week's tutorial. They'll certainly be available for our next tutorial. So you should be working through all of these exercises here. If you encounter any problems with them, you're unsure, you need something clarified, do bring those questions and queries to your tutorial. Okay, okay, so we'll proceed on to the next section now, which is about the chain rule. Now the chain rule, as just a title and a name, of course, is familiar to you because we have something in one variable calculus called the chain rule. Okay, one way you might have known this, well, it's typically presented in two types of notation here. But the chain rule is something that allows you to take the derivative of a compound function. A complicated function, which is the composition of two or more simpler functions. Okay? So some situation where you've got y as some function of x, but then x isn't just a kind of atomic variable itself. Maybe we have x expressed as some function of another variable t. So y there is the composition of f and g applied to the input variable t. So really, fundamentally, y is a function of the variable t, so we'd like to be able to express the derivative of y with respect to t in terms of the derivatives of the component functions, f and g. Okay? That's what the chain rule allows you to do, and it's quite in this kind of d over d notation. It's normally expressed like this. dy dt is df dx multiplied by dg dt, or in some kind of alternative notation, to differentiate the function y applied to t, well, y is a composition, f after g of t. The rule for doing that is you differentiate the outer function, you evaluate it at the original input. So you write this as x of t, or alternatively, you could also write that as g of t, they're the same kind of quantity, and then you multiply by the derivative of the inner function. Okay, so that will be familiar to you from previous years. And there it's only shown expressed as it applies to a composition of two functions, but equally well it applies to compositions of 3, 4, any number of functions. You perform the differentiation of the compound function by working from the outside in, differentiating the outside function, evaluating the derivative at the same argument, and then multiplying by the derivative of the next function in. You keep working down until you reach the actual independent variables that are mentioned. So the obvious task ahead of us is to generalize this concept to functions of more than one variable. Okay? We've already seen how the concept of differentiation generalizes to partial differentiation. So what goes on with the chain rule? Okay. So here is how we kind of set the problem up. So we suppose we have some function f, and it could depend on any number of variables. So f might be a function on the variables x1 through to xn. But suppose there's an alternative system of coordinates for Rn. Okay. So we're going to imagine, rather than describing points in the plane as points in the space Rn as combinations of the coordinates x1 through xn, instead you're going to describe them as combinations of z1 through zn. We'll meet a concrete example soon. The general setup is, well, we will know what the functional relationship between the new variable z and the old variable xi is. So for each variable xi, the ith old variable xi, we will know that as a function of the new variables, z1 through zn. Then the aim would be how to express the partial derivatives, dy dzi. We only start off with y is expressed as a function of the x's, f of the x's. But now we want to know what the partial derivatives will be of the function y with respect to these new variables, z. And what we're expecting is some kind of rule which will tell us what this partial derivative is in terms of the partial derivatives of our original function f and partial derivatives of these functional relationships ui here between the new variables and the old variables. Okay? So the functions ui here are playing the role of the function g in the previous one-dimensional example. Okay? So that's the kind of setup. Well, let's just make it a bit more concrete and just look at a particular example. So this is a two-dimensional example. So everybody's familiar with the Cartesian coordinates x and y for describing the location of points in a plane. And I'm hoping you're somewhat familiar with polar coordinates. But polar coordinates are sometimes called circular coordinates for the plane. This is an alternative system for referencing the positions of points in the plane. And you don't do it by giving its kind of east-west displacement and the north-south displacement as you do with the x and y. Rather, you give it an angle where the point is located on a radius starting from the positive direction of the x-axis. So describing what the correct angle is in order to obtain the point on a radius from the origin. So theta determines a line containing the point P going through the origin, and then the value of the radius r will determine how far out along that line you need to go until you hit P. Okay? So instead, we can equally well locate the point P by giving the value of this angle theta and the radial distance r. And that locates the point P just as good as giving the x and y east, west, north, south coordinates of the point P. And we also know exactly how these two systems, x, y, and r theta, are related. Okay, through these equations here. These equations, you could quickly rederive them by considering the obvious right-angled triangle there, involving r as the hypotenuse and x and y as the other two sides. So we get x as r cosine theta and y as r sine theta. Okay, so that's just a concrete example of a two-dimensional coordinate system xy and an alternative two-dimensional coordinate system r theta. And we'll return to that example shortly for one of our illustrations of the chain rule. Okay, so what is the chain rule? Well, it comes from the small increments formula. So we're back to a general discussion here now in 1.78. We're dealing with a situation of a function of two variables. But quite often with this stuff, it's enough to kind of go through the theory in the two variable case and then just talk about the obvious generalizations to more than two variables. So we have a function z depending on x and y. But we also understand that x and y themselves depend on an alternative system, s and t. Okay? We can kind of regard x and y as the old variables and s and t as the new variables. We know how x and y are connected to s and t through these two functions, u and v. And we know how z is connected to the value, how z is connected to the old variables x and y. That's through this function f. Okay? What we want is partial derivatives of z with respect to the new pair s and t. That's what we seek to obtain. Okay, well, just by substituting for the variables x and y, we can easily come up with the function for how z depends on s and t. And you can see here it does have the natural form of a composition, because we've substituted for x and y, u of s and t, and v of s and t. So we clearly have z is the function f after the functions u and v have been applied to the input variables s and t. So that equation 1.79 is showing how z is expressed as a function of s and t. And now we seek to express the partial derivatives of z. But we start off with the small increments formula expressed for the change in z in terms of changes in x and y. So this is just exactly the same small increments formula we had a few pages ago. Delta z is df dx delta x plus df dy delta y. So this is an approximation for the change in z brought about by changes delta x and delta y. But now what we do is we divide this expression across on both sides by the quantity delta x. So we get this new expression. We have a ratio of changes here, delta s, delta z over delta s. We still have these coefficients of partial derivatives, df dx and df dy. But now here we have two other ratios of changes, delta x over delta s and delta y over delta s. That's equation or approximation 1.81. And then we take the limit as delta s goes to 0. Remember, we're after expressions for partial derivatives here. With respect to s, so we should be taking a limit of this as delta s approaches 0. And what we had on the left-hand side of this approximation, we had delta z over delta s. And taking the limit of that as delta s approaches 0. Well, that is exactly the definition. By definition, that is exactly what delta z over delta s is. That is exactly the partial derivative of the quantity z with respect to s. Okay? So we're looking at the change in value of z as a ratio of, as a proportion of the associated change in value of the quantity s. And taking the limit of this as delta s approaches 0, that's the definition of this quantity delta z over delta s. On the right-hand side, we had the partial derivatives delta f, df dx and df dy. Those remain unchanged. But on the right-hand side, we had delta x over delta s. And taking the limit of this as delta s goes to 0, well, if you look at that, that's exactly the definition of the partial derivative of x with respect to s. Similarly, with the other ratio changes, delta y over delta s, taking the limit of that as delta s goes to 0, that's the definition of the partial derivative dy dx. Also, since we're taking the limit as delta s approaches 0, that approximation, which is provided by the small increments formula, that will actually become a straight equality in the limit. Okay? The small increments formula gives better and better approximations as the changes in the variables get smaller and smaller. So what are we looking at now? See, we're looking at now, this is what we kind of set out to find. So on the left-hand side, we have the partial derivative of z with respect to one of the new variables. And on the right-hand side, we've got the kind of already known partial derivatives of f with respect to the old variables x and y, combined with the partial derivatives of x and y with respect to that new variable s. Okay, so on the left, it's the new partial derivative of z, expressed in terms of the old partial derivatives of z, df dx, df dy, and the partial derivatives of the functional relationship between the old variables and the new variables. Okay? So it's kind of the new in terms of the old, and the link between the old and the new. Okay? So we can refer to 1.82 as one of the chain rule equations. Whereas in the one variable case, you had a single chain rule equation. In the two variable case, we're going to have two chain rule equations. This is one of them with respect to the variable s, but there's also the other new variable t. So in exactly the same way, you can start with the small increments formula at the bottom of the previous page, this one here, and now divide across by delta t. But it works exactly the same as it did in the s case. When you divide across by delta t, take the limit of both sides as delta t goes to 0. All these ratios of changes in the limit, they become the appropriate partial derivative. And we end up with this equation here, which exactly mirrors the structure of the s one here. And this is the second chain rule equation for this situation of two variables. This tells us what the partial derivative of z with respect to t is in terms of the known old partial derivatives of z, df dx, df dy, and the partial derivatives of the relationship between the old and the new variable. So definition 1.5 just kind of restates all of this and collects them together. Just looking at the two equations beside each other. And it's not too hard to see that what the pattern is, and to make a generalization to more than two variables. In the multivariable case, so here's the chain rule for two variable functions. Here's the chain rule for n variable functions. So you got z, as we said before, z is a function of some old variables x1 through xn. We've got a new system of coordinates s1 through sn for the domain. We know the functional relationship that takes you from the new to the old. These are these functions ui. Then the chain rule equations are these n equations. Now these equations are indexed by I. So we have one of these equations for each value of I. On the left-hand side, we've got dz with respect to the ith variable si. So the partial derivative of z with respect to the ith variable si. On the right-hand side, we've got a sum over j. So this is summing over the index j. This is going over all the old variables, x1, x2, x3, and so on. And we're taking partial derivatives of each of those old variables, but always with respect to delta si. Okay? So we've got one of these equations for any value of I. So for any particular one of these equations, I is fixed at some quantity between 1 and n. Say 2, I equals 2 on both sides. But j is always running over all of the old variables. Okay? Just as in the s1 in the two variable case, you've got delta x ds, dy ds. For delta t, you've got dx dt, dy dt. You've got the derivatives of each of the old variables in terms of this one particular new variable, which is indexing the equation. Okay. Okay, so let's have a look at this example. Might just for the purposes of talking through it, I might just, oh no, I won't. Just talk through it on the page. First of all, any questions first, before we look at this example? This example should help to make it feel a bit more concrete. But any questions just about the structure of it? So it's the generalization of the one-dimensional chain rule. And it's helpful, or it applies, it's relevant in situations where we have an already established set of coordinates for the domain of a multivariable function, and where we're changing to an alternative set of coordinates. Okay? In various situations, we quite often chop and change around between different coordinate systems because different coordinate systems are useful for different situations. And it's not hard to appreciate how, if you're studying some kind of situation which involves some kind of circular motion around the origin or around a central point, well, the Cartesian coordinates are a bit clumsy for talking about circular motion around a center point. You end up having to talk about expressions in x and y involving the square roots of the sums of squares. It can be awkward. Whereas the polar coordinates are naturally built for talking about circular motion, because they include the radius of the circle as one of the quantities, and this other quantity is the angle theta. Very natural interpretations, just where, how far around in the orbit the thing is around the center. So for any kind of situation where there's a strong circular component or strong circular features in the situation, in the two-dimensional situation, it's quite often a lot easier to analyze it in terms of polar coordinates. That's why you might prefer the polar coordinates over Cartesian coordinates. In other situations, the Cartesian coordinates will be the most useful. So let's look at this example down here. So this example is about the situation where you've got Cartesian coordinates x, y for the plane and polar coordinates r and theta. And what we've got here is we've got this expression here, so I've just called it curly f, like a script handwriting f. So this is some kind of differential expression in terms of Cartesian coordinates and some function f of the two variables x and y. So it's x times df dx plus y times df dy. This might be an expression that appears in a partial differential equation, governing the motion of a fluid or something. And our task here is we want to just take this expression. It's not really an equation. The equation bit is just, I'm attaching this label, curly f, to this expression. Take this expression and instead translate it into the polar coordinates r and theta. So I want to really remove any explicit reference to the Cartesian coordinates x and y and replace everything and instead speak in terms of the polar coordinates r and theta. And the device that allows us to do that is the chain rule. So I've got these two quantities. I mean, I know how to replace x and y. X and y would be replaced by r cosine theta and y replaced by r sine theta. The trickier things to replace are these partial derivatives, df dx and df dy. But I can immediately write down the chain rule. Okay? So the chain rule for the x variable says df dx is going to be df d theta dx plus df dr dx. So that's the expression that takes a partial derivative of f with respect to x and replaces it by information about partial derivatives with respect to r and theta and partial derivatives of the functional relationship between r theta and xy. Now, tackling the various parts of that, well, we need these equations here which tell you what r and theta are in terms of x and y. So these are the kind of inverses of the cosine and sine relationship. Because I want to work out these partial derivatives, d theta dx and dr dx. So I need these expressions for r and theta in terms of x and y for that. So r is the square root of the sum of the squares. Theta is the inverse tan of y over x. So I can take those partial derivatives then. dr dx will be x over r. Well, you have to do a bit of work for that. Dr dx, you have to apply the one variable chain rule. It's going to be a half of the sum of squares to the power minus a half. So the sum of squares to the minus a half is this 1 over r here. And then it's multiplied by the derivative of the inner bit with respect to x, which will be 2 times x. So the 2 you get on top cancels that factor of a half that came from bringing down that index, and you're just left with x over r. Then we can make use of the known formula for the derivative of the inverse tan of something, which is 1 over the square of the something plus 1. We can use that in combination with the one variable chain rule to take the derivative with respect to x of inverse tan of y over x. Okay, so it comes out after a little bit of simplification as minus y over r squared. So taking those quantities for the partial derivatives and substituting them back into this original chain rule equation, so I've got d theta dx and dr dx now. So putting those back in there gives me this expression here. df dx is minus y over r squared df d theta plus x over r df dr. Now I've still got x's and y's appearing here. I might be able to get rid of those in a moment. You would then turn to the other partial derivative, df dy. Again, applying the chain rule, so we'd start with the equivalent thing to this expression here, but talking about df dy. So we've got these y partial derivatives here, d theta dy and dr dy. Using similar techniques to what we've just done, d theta dy comes out as x over r squared, and d theta dr comes out as y over r. And we have these expressions here. So finally, we can assemble curly f, which was x times df dx plus y times df dy. And the introduction of these new factors of x and y combine with what we've got here to give us, well, you see, you get some cancellations. When you multiply this by x, you get a minus xy over r squared. You multiply this by y, you get a plus xy over r squared. They're both multiplying df d theta, so those will cancel out. And we'll just be left with x squared plus y squared over r times df dr. But of course, x squared plus y squared is the square of the radius. That is the quantity r squared. You get r squared over r, and a final simplification to r df dr. Okay? So this is our nice final expression for our original partial derivative expression in terms of Cartesian coordinates. And it translates into something quite nice and compact in the new polar coordinate system. That's one example of how we might use these chain rule equations. Now, one final thing, I should have asked you when we first looked at it, but this, you look at the two variable case, this set of equations here, especially since you're doing linear algebra with Stephen, this should evoke something in your mind, just seeing this kind of pattern here of a set of equations and, you know, quite similar entries here getting multiplied together. This kind of reminds you of matrix multiplication, okay? It looks like these entries here come about from multiplying a column term by term into, or multiplying two vectors together term by term, taking the dot product of two vectors here, these expressions on the right-hand side. So, and that is indeed the case. Those equations there can be put into matrix form. And when you do that, we see the appearance of this special matrix which we call the Jacobian. The Jacobian matrix is the matrix of partial derivatives of one coordinate system with respect to another. So one way expressing those chain rule equations we looked at in the two variable case, we can say the row vector of new partial derivatives of f, so the row vector df ds, df dt, is equal to this product of the row vector of the old partial derivatives multiplied by this matrix. So this matrix is, in a sense, a transformation matrix from the old coordinate system to the new coordinate system, which carries partial derivatives to partial derivatives. And it is itself a matrix, a 2x2 matrix of all the possible partial derivatives you can do with respect to differentiating x and y with respect to s and t. Laid out very carefully and precisely. If you multiply these two matrices here and equate them with this row vector here, you do recover exactly the two chain rule equations we put down previously. So this matrix is termed the Jacobian matrix. If you say the word Jacobian itself, it's normally understood that you're referring to the determinant of this matrix. But people also use the word Jacobian to refer to the matrix. And you can clear up any ambiguity by talking about the Jacobian matrix or the Jacobian determinant as appropriate. And we will see it arise again shortly in a lecture or two. It's an important device which will describe the behavior of these different coordinate systems. Okay, so there's a whole bunch of tutorial exercises there on page 17. And I've also got a bunch of extra examples here I'm going to hand out. And I might use some of these in the lecture this evening that I have with you. Do some more concrete work with some examples. So I'll just get these out to you before you go. Yes. What's your name? Sorry,